Dear ladies and gentlemen, welcome at my presentation about the fatigue of multiaxially loaded shrink-fit connections, especially with the focus on the material effects. I am a PhD student at TU Chemnitz in Germany at the Design and Drivetrain Institute. First of all, I would like to introduce the main character. It is a shrink-fit. Shrink-fit is a shaft-hub connection which is established by expanding the hub, by heating it, and then shrink it on the shaft by cooling back to the room temperature. Resulting from this, we obtain some contact stresses by which we are able now to transmit the operational forces within some friction loads. Typical loads for the drivetrain components is rotating bending and torsion. And yes, considering these loadings in engineering level approach, we are using notch factors for both components, and basically they are experimentally estimated, determined. And in the case of the combined load, we are using, for example, within the German standard DIN 743, we are using some safety formula which is combining these loads in terms of nominal stress divided by the strength. And as you know, this is a similar, quite similar formula like the Goff ellipse. Based on our experience, we have found out that this combination, especially for contacted components, leads to some critical estimation of the fatigue, and it's caused by the interaction of these channels. That means that the bending is affecting the notch factor of torsion. So, of course, we are able to manipulate this formula, for example, by changing these exponents, but our objective is to, long-term objective, I would say, is to have a local approach for calculation of fatigue limit of shrink-fitted shaft-hub connections. So let's take some look on experiments and then to the fatigue calculation. First of all, to apply such loads, we have developed test bench which is pretty unique. We are able to independently independently apply bending and torque channels in this setup, and by this we are able to adjust several parameters like frequency ratio, amplitude ratio, the torsional misstrength, of course, phase shift. As the title says, we are investigating the material effect, so we decided to choose one constellation of these parameters at one amplitude ratio, which is of equal amplitude and of equal frequency. Apparently it looks like a proportional load, but if we take a closer look to the load kinematics, we will recognize that we will obtain different phase shifts over the circumference of the shaft, independence we will obtain a different phase shift on the circumference even at equal frequency ratio. You can see that on these lines. Red one is the bending, blue one is the torsion. At position of 0 degree we have the proportional case, and at position of 90 degree we have the alternating bending torsion state. So the circumferential position corresponds to the phase shift. Okay, so we have even non-proportional state at proportional loadings, and as a result we have some highly stressed areas. I will come back in the future slides. For the material comparison, we have chosen a quench and tempered steel 42 chromo 4 and a normalized steel C45. And additionally to the shrink fit connection, we also tested some filleted shafts without contact, so we could separate the tribological effects and determine the known material sensitivity of the structure, which is already known. Okay. I already come to the results of the experimental investigations. We have tested with staircase method with a cycle limit of 10 million cycles for shrink fit and 5 million cycles for the free surface specimen, and as a result we obtain an endurance limit with the survival probability of 50%. First of all, the results of the filleted shaft shows that there is a clear material difference between these two materials. But if you take a look at the experimental results of the shrink fit, we can see that the absolute level of the higher strength steel is approximately the same than the low strength steel. So the material sensitivity is much higher than the known structural sensitivity. Okay, let's take a look to the fracture surfaces. Remember the picture of the highly stressed areas. We obtained, for both materials, we obtained the cracks at the position of 0, respectively at 180 degrees. And in the closer look of the shafts, where we have disassembled the hub, now you can see down is the free surface, and up this line we have the contact surface, and with the tribological degradation. But it was interesting, we have found out that for C41 we have crack initiations really in the vicinity of the hub edge and growing in direction of the free surface. But for the high strength steel, we have a lot of crack initiations within the contact and staying there. So this could somehow underline the material sensitivity to fretting fatigue. Yes, due to unsymmetric loading, we have to deal with 3D FA model, which is pretty challenging because we have to refine the mesh in properly way that the simulation times are low, and of course our input are the loads and conditions from the experiment. We have some material definitions, contact definitions, and so on, and resulting from this simulations, we obtain a stress state which is the input for our multiaxial fatigue analysis. For the multiaxial analysis, I choose 4 hypotheses of integral approach, which is a pretty good known SIH, then the PIN, and brand new hypothesis BO. Let's say these 4 hypotheses are very similar, and the approach is based on cutting planes, but in contrast to the critical plane approach, you are not choosing a critical plane, but you are integrating over all planes, and then building, and then you are able to calculate the equivalent stress. Back to the brand new criterion. This is a promising one for us because it was developed for case hardened steels or components, and this contributes similar conditions than the context because they have also compressive mean stresses in the structure. Yes, and I compared this criterions within a small study. I have some backup slides if you are interested in that. And the best or the smallest calculation error it was reached with the BO2. For the where we are evaluating this stress, considering the stress gradients, and also that it is pretty hard to locate the crack initiation, we decided to evaluate the stress in context of theory of critical distances. That means we are evaluating this stress in a critical distance, and for the uniaxial case, it is pretty good known that this critical distance lies somewhere at the half length of a non-propagating crack. These formulas, I think, you know from El-Haddad. But there is a question: what is the critical distance in multiaxial case? There are some points about the. No, sorry. There are some questions about the thresholds values for the mixed mode regime, and there are already some. Sorry. There are already some approaches for this, but there is another question about the determination of thresholds in mode 3, which is pretty complicated and lead to the pretty high critical distances. And also it is questionable what is the influence of contact to the threshold values, as you can see in the pictures. So our idea was to inverse search for this critical distance within the numerical model, using this appropriate model according to Böhme. Now we can see already the first results. We evaluate at position 0 degree, and we see here the stress fields for C45 and 45 chromophore, quenched and tempered. And now we see the plot of the equivalent stress according to the BO criterion, and now we are looking for a place where the critical, looking for a position or for critical distance where the equivalent stress corresponds to the fatigue limit. For this purpose, I plotted several paths. First for the C45. As I mentioned, the crack location of C45 was quite to the hub edge, and therefore I started there 2 paths. And if we now read the fatigue limit, which is about 250 megapascal, we reached for this path a critical distance for 70 microns. Yes. As I was writing the abstract, I was accepting that we are able to consider these material effects which I described by lowering the critical distance. But after the evaluation of the simulation, we found out that the fatigue limit of the higher strength steel is even higher than the stress gradients are.
1 minute to finish.
Yes. This is the result. I was quite upset, but yes. Okay. Then I would like to summary. I'm glad to show you some small part of our investigations. Here the focus was on the material sensitivity. I would say we see in experimental investigation that the sensitivity is high in fretting fatigue, and with evaluation we have estimated critical distance for the shaft from normalized steel, which lies in a plausible scope. but we were not able to estimate this for the other steel. So the material sensitivity couldn't be covered by this method. And that leads me already to the outlook. So I see two ways to deal with this problem. One is to go back to the crack initiation. That would mean that we should consider some tribological parameters in the criterion, like Mr. Knabner, my colleague, told us yesterday. But in the other way, if we are staying at this approach with thresholds and so on in theory of critical distances, we have to improve the numerical methods. Means maybe we could use some critical plane methods for better defining the crack paths, and also we need better thresholds, for example, in presence of contacts. And we hope then that we can evaluate far more experiments that are on our table. So, thank you for your attention, and thank you for the sponsors.
Thank you for your